All right, sorry, friends. Someone knocked at my door and I got interrupted. But rather than repeat everything again, I'm just going to pick it up right here. So there'll be two videos for this, but they're all for the same worksheet. All right. So when I reach equilibrium after this addition of acid, I have a 0.0025 moles of that base, zero of the acid, 0.0015 moles of the KNO3, and 0.0015 moles of water. All right, so I look at these three components that are present in my solution and I ask myself, do any of these influence the pH? And if so, is any one of them more influential than any other? All right, so I could make an argument for the KOH, obviously, and the water. All right, that KNO3 is going to split into potassium ions and nitrate ions, both of which would be considered conjugates of strong acids and bases. So they will have no influence on pH. They're way too weak. All right. Of the two that might influence it, the strong base is going to be the most influential, right? So I'm not going to consider the water, all right? Instead, I'm going to look solely at the amount of hydroxide that is present, okay? So this is in moles, so I need it to be in molarity. So molarity is moles divided by volume. So I have 0.0025 moles of KOH, and that is present in a total volume of 55 milliliters. So that's 0.055 liters. So the concentration of KOH remaining is 0.045 molar. Now this is less than the 0.1 molar I started with, which makes sense because some of it has reacted with that acid. Okay, now what do I do with it? Well, I know that KOH dissociates into K plus and OH minus 100%. All right, so that means that this value is also equal to the concentration of hydroxide that is present. So I'm going to use that value to calculate the pOH of this solution. So the log of the concentration of OH minus, which means the negative log of 0.045 molar. So I get a pOH value here of 1.35, but I need the pH. So it's 14 minus that pOH value, which is going to be equal to 12.65. All right, so our pH has decreased from what we calculated for A, which is reasonable because we have used up some of our base. We have less base present than we did in part A. So we should see a slight decrease in that pH value as it becomes a little bit less basic. Okay, so that is a very reasonable answer. All right, let's move on to step C, or part C. All right, now we're going to have added 40 total milliliters of 0.1 molar NaOH. All right, so again, I'm going to use moles. So moles of base is still what it was before, 0.0040 moles, because we haven't changed the amount of base. We haven't added any base or removed any. That's what's present. All right, and then for the acid, moles of acid is going to be molarity of the acid times the volume of that acid. All right, so we're going to have 0.1 molar times 0.040 liters. All right, so that's going to be 0.0040 moles. All right, so the moles of acid present, 0.0040 moles. Now, when I look at that, hopefully my brain says these are equal. So this should be our equivalence point. All right, which means, hopefully, that the only thing left after the reaction is water. But we should make sure. All right, so we have KOH reacting with nitric acid, all right, forming our salt, potassium nitrate, and water. All right, we set up our ice chart. Initially, I have 0.004 moles of base, 0.004 moles of acid, no salt, no water. Now the change, they're both the same. So we subtract 0.004 from each, and then we add 0.004 to each. All right, so we don't have any base left, we don't have any acid left, and we have 0.004 moles of KNO3 and 0.004 moles of water. All right, so we think about what might influence pH. Well, again, the KNO3 is a salt, and those are anions and ions of strong acids and bases, so this is going to have no effect. So the pH would depend only on water. All right, now it's already in a bunch of water, so it's not really 0.00 moles of water total. All right, that's the additional water that's been added. All right, and we know that when we have pure water, the pH of that solution must be 7. All right, so we use the pH value of 7 at the equivalence point. All right, we're going to end by adding a total of 55 milliliters of that 0.1 molar acid. So again, the moles of the base are going to be equal to that 0.0040 moles we had to start with. All right, and then our moles of acid are going to be the molarity of the acid times that volume of the acid. So 0.1 molar times 0.005, 55 liters. So we're going to get 0.0055 moles of acid. All right, so moles of acid equals 0.005, 5 moles. All right, so hopefully you notice that the moles of base are less than the moles of acid at this point. All right, so I would expect that the pH of this solution, when I'm finished my calculations, is less than 7. All right, so again, KOH plus nitric acid, forgot my hydrogen, yields KNO3 plus H2O. All right, ICE, initially 0.004 moles. And for the acid, 0.0055 moles, no salt, no water. All right, so now we look. The base amount is the lesser, so that's what's going to get lost. 0.0040 minus 0.0040, and that's what's going to get made. 0.0040, 0.0040. All right, so we have no base left, and we'll have 0.0015 moles of that strong acid left. We'll form 0.0040 moles of our salts and an additional 0.0040 moles of water. All right, so again, I look, that salt has no influence, so I'm left with strong acid and water. All right, well, strong acid can have a much stronger influence on our pH calculation, so that water is going to be irrelevant at this point. All right, so I need to know the molarity of my acid. All right, so that's going to be moles of acid divided by our total volume. All right, so 0.0015 moles. All right, I started with 40 milliliters of base, and I have now added a total of 55 milliliters of acid. So my total volume is 95 milliliters, which is 0.095 liters. So my molarity here is 0.016 molar. So that's the extra acid that is still present. All right, HNO3, it's a 1-to-1 ratio of the acid to that H plus ion. All right, so this equals the concentration of H plus. All right, so then our pH is the negative log of that value. So the negative log of 0.016 molar gives us a pH value of 1.80. All right, and I asked myself if that's reasonable. Yes, I have strong acid present. I should have a very low pH value, which is what I see. So this is reasonable because we have excess H plus ions. Okay, so you can see the 4 steps. The first step, no acid added, very low pH because strong base controls that pH value. Step 2, addition of some acid, so we neutralize some of our strong base, but then we have excess base present, and that determines the pH. But we do see a slight decrease in that pH because we have less base present than we had in the first step. For step 3, we're at the equivalence point. We have the equal amounts of moles of acid and base. All right, so when they fully neutralize after the reaction, there's no acid, no base left. The only thing present that has any influence on pH is water, and we have a pH of 7 there. And then we end by adding an excess of strong acid, so we neutralize all of the strong base. So the only thing left in solution afterwards that influences pH is going to be our strong acid, and that gives us a very low pH value. So all of our answers are reasonable here. All right, sketch the titration curve for this experiment. All right, so we're going to start. All right, this is the pH, and this is acid added and milliliters. All right, so 2, 4, 6, 8, 10, 12, 14. All right, and then down here, I'm going to do these by 20. All right, 20, 80, 90. Oh, wait, oh, hold on. Oh, messed up a little bit here. 20, 40, 60, 80, 100. All right. All right, now, this sketch is going to be just a sketch. I won't have determined pH values at every single data point, so I'm going to fudge it just a little bit. If you were running a titration with a titration probe, you could, after every addition, determine the pH, and then you would have a nice curve. But we're just going to look at the 4 different stages. All right, so stage A, base only. All right, so at that point, the pH was 13, so no addition, so we add that data point. Section B, excess base remains. All right, so after the addition of 15 milliliters, we had 55 total, and we had 12.64, so that's going to put us right around here in terms of a data point. All right, so you can see that there has been a slight decrease as we go towards that addition. All right, but we do have excess base in solution, so we're going to have a very high pH. C, at the equivalence point, moles of base equals moles of acid. pH equals 7. All right, so that was after the addition of a total of 40 plus 40, 80. So we're here, and there's 7. All right, so it probably comes down a little bit more and then shoots down just like this. All right, and then D, we have excess acid. All right, and that was at 95, and we saw that the pH was 1.8. So here's 90, 95, so right around here. All right, so I would expect to see it, and then if we kept going, it would probably continue to decrease a little bit. All right, so here's A, no acid added, base only. Here's B, where we see a decrease in pH because we've used some of our base in reaction with the acid. C, our equivalence point, where the pH is equal to 7 due to water because we've fully neutralized our base with our acid. And then D, excess acid present. All right, so you can see the shape of that curve is similar to what I drew at the beginning. Okay, so practice. All right, if you're given it the other way, a strong acid with a strong base addition, calculations are going to seem very similar. Set it up the same way. Just remember that your titration curve is going to start low and go high if you start with an acid and then neutralize to excess base. Okay?